Hey, 17C students, here are the solutions to the practice exam for the class. First one says find and sketch the domain of f of xy equal to the square root of 9 minus x squared minus y squared divided by the natural log of y minus 1. There's a few things we have to consider here. First, let's look at the top. We need 9 minus x squared minus y squared to be bigger than or equal to 0, right? Because square root of a non-negative number. So then I would isolate x squared plus y squared, so write it as 9 bigger than or equal to x squared plus y squared, or x squared plus y squared less than or equal to 9. We know that's everything inside the circle of radius 3 because we can see that like 0, 0 would satisfy this, or 1, 0. We also need a couple things from this natural log here. So for the natural log of y minus 1, we need first y minus 1 to be greater than 0, or in other words, y greater than 1. We also, and this is the tricky part here, we need to make sure that we're not dividing by 0. So we also need for the natural log of y minus 1 equal to 0 to be excluded, which means e to the 0 equals y minus 1, or 1 plus 1 is equal to y. So y can't be 2. Okay. As far as writing this out, it's kind of a pain. I guess yeah, so I would just really just draw it. So I want to be everything inside the circle of radius 3. But I want y to be bigger than 1. So that means I have to be above the line y equals 1. So I can draw this out here. So 1, 2, 3. So here's y equals 1, which I don't want to include. I also don't want to include y equals 2, but we'll deal with that in a second. And then my circle of radius 3 would look like this. Same kind of a deal. Right, it would continue on that way. But I don't want that part. And then I don't want y equals 1 either. So I want everything above y equals 2. And sorry, above y equals 1 and above y equals 2. It's still inside the circle here. So I don't want this dashed line here. It's kind of hard to see. I don't want that dashed line down there. Interesting. Yeah, kind of a pain. So I would maybe write y equals 1, y equals 2. These are both getting excluded. If it's not clear from your drawing, you can always just write the words. Yeah. Nice. That's kind of it. So everything inside the circle of radius 3, but above the line y equals 1 and not including the line y equals 2. Yeah. An interesting kind of variation on this would have been if I had said the natural log of 1 minus y, and then we would have the below part instead. So we'd want 1 minus y to be bigger than 0, which would mean y would be less than 1. And then we would also have to exclude whatever made the whole bottom equal to 0 as well. Yeah, in fact, you should try that on your own. I would encourage you all to try the same thing, except it would be f of xy equal to the square root of 9 minus x squared minus y squared. And your denominator now is the natural log of 1 minus y. I would encourage you to try that and see what you have to exclude. All right, let's do the second question here. Let h of t comma r be the heat index where t is the temperature and r is the humidity. The rate of change of the heat index h with respect to t is 5. Okay, so when I read that, the rate of change of the heat index, so the rate of change of the heat index h with respect to t is 5. So that's telling me that del h del t is 5. And the rate of change of the heat index h with respect to r is 3. So del h del r is equal to 3. I feel like this pen is not writing very well. Let's grab another one here. Sorry, one that still is. I haven't actually put it in my other bag there. Okay, 1 second. Sorry, let me grab the pen. Apologies. Oh, terrible, I know. You can fast forward this part later. So, sorry about that. Let's see here. Cool. All right, here we go. So that's 3. And then They're asking, what is the rate of change of h with respect to time? So we're asking to find dh dt, little t. Um, what is the rate of change of h with respect to time? If the rate of change of capital T with respect to time is -1, so they're telling us that dt d little t is -1, and the rate of change of r with respect to time is 4. So dr d little t is 4. So this is a chain rule problem where they're kind of giving you all the information in kind of a roundabout way. So let's draw a little map. We know that capital H is a function of temperature and humidity, and then temperature and humidity both depend on time. So we can say that dH dt, little t, is equal to, well, all the paths that get us there. So h to t and then t to t. So del h del t times dt d little t plus the other path, del h del r times dr d little t. Then we just plug in the numbers. So del h del t is 5, dt dt is -1, and then del h del r is 3, dr dt is 4. So I'm getting -5 plus 12, which is 7. 7 what? I don't know. They didn't really give us any units, so we just say 7. Cool. Moving along. The average energy E needed for a lizard to travel a distance of 1 kilometer has been modeled by the equation. Energy for a certain mass and velocity or speed is equal to 2 times m plus 3 times m divided by v, where m is the body mass and v is the speed. Find the linearization of the energy function at a point of your choice. Choose wisely and use linearization to estimate E of 61, 3.1. So we first have to figure out what point is close to 61, 3.1 that's easy to plug into this function. You might think 61, 3 is the right choice, and that's not a bad choice, but I'll point out if you plug in 61, 3, look what happens. You're going to get 2 times 61 plus 3 times 61 divided by 3. That's actually not a terrible choice. I was thinking of making a different choice, but yeah, the problem here is that the 3 cancels out super easily. Yeah, fine, we'll do it that way. So that's going to be, let's see, 2 times 61 is 122, and then plus another 61 is going to be 183. I was really thinking I was going to plug in 20 instead of, or sorry, 60 instead of 61. But 61 probably is going to work out just fine. All right, so linearization, right? The linearization of a function is going to be the function evaluated at the nice point plus the partial derivative evaluated at the nice point times your variable minus that corresponding value. And then the partial derivative the other partial derivative evaluated still at the nice point. And then it's your other variable minus the corresponding value. So our job to kind of fill this in, well, we know that's going to be 183. We still have to find our partial derivatives. So the partial with respect to m, and I would probably rewrite my equation here as 2m plus 3 times m times v to the -1. Sure. So my partial with respect to m is going to equal 2 plus 3 times v to the -1. Or if you prefer, 2 plus 3 divided by v. So if I plug in my point, so if I plug in 61, 3, it's going to be 2 plus 3 divided by 3, which is 3. A lot of 3's. And then my partial with respect to v is going to equal 0 plus 3m times -1 times v to the -2. So it's going to be 3 times m times -v to the -2. Or if you prefer, -3m over v squared. And if we plug in our values, here the values might get kind of funky. Here's where 60 might have been the better choice. Let me look at my notes over here real quick. We might go back and change our choice. Totally fine. Look here real quick. Yeah, that's where things are going to get gross. So here's where we're going to go fix our choice. So if you plug in, problem here is if you plug in 61 and 3 times 60, well, 3 times 61 divided by 3 squared is not very nice. So let's go back and fix our guess here. And I knew there was a reason I wanted 60 instead. So I want 60 instead, sorry. So 2 times 60 is 120. And 3 times 60 divided by 3 is 3 times 20, which is still 60, or just 3's cancel, James. I can be smarter about that. That's going to be 180. My notes over here. Yeah. So that's going to be a 180 here, not a. Apologies for all the changing. So I suppose in retrospect, it would have been better to find my partial derivatives before I started trying to pick the nice value to plug in to see how things are going to work out better. So I would say if you're doing linearization and they didn't tell you what point to linearize around, it's a good idea to look at your partial derivatives and see what's going to be a nice thing to plug in. Usually it should be relatively obvious. I could have made this more obvious by making this like 60.1, but I didn't. That's going to be 60. So this doesn't change anything here, right? Plugging in 61 or 60 for M. Well, there wasn't an M to plug into here, so we still got just 3. But here, this is going to be a little bit nicer. If I plug in 60 comma 3, I'm going to get negative 3 times 60 divided by 3 squared. Negative 180 divided by 9 is negative 20. So now my linearization is going to equal 180 plus my partial with respect to M at the point, which is 3, times M minus 60, plus my partial with respect to V, which is negative 20, times V minus 3. After we have the linearization, that's when we then plug in the actual point we have. So then we're going to say, great, my actual function E of 61 comma 3.1 is going to be approximately my linearization with 61 and 3.1 plugged in, which is going to be equal to, I'm just going to plug in 61 for M and 3.1 for V to get 180 plus 3 times 61 minus 60 plus negative 20 times 3.1 minus 3. That's going to be 180 plus 3 minus 20 times 0.1 is 2. So we're going to get 181. I will point out, what was I going to point out? Sorry. There was a thing I was going to point out here. Brain. Oh, I know what it was. You don't want to simplify this, right? It's not a good idea to write this as like 180 plus 3M minus 180 plus negative 20V plus 60. Like usually that's not going to be worth your while. You just want to leave it as is and then plug in the points that are close to where the linearization is. All right, let's look at the next one. Consider the function f of xy equal to x cubed times y plus 2x plus y squared. What is the maximum rate of change of f at the point 1, comma 2? Great. Maximum rate of change of a function is just the magnitude of the gradient at the point. So the gradient is just the vector fx comma fy, which is going to be, let's see, the partial derivative to x is going to be 3x squared times y plus 2. The partial derivative to y is going to be x cubed times 1 plus 2y. Then we plug in the point that we're actually finding the gradient at. So the gradient evaluated at 1 comma 2 is going to be the vector. We're plugging in 1 for x and 2 for y. So it's 3 times 1 times 2, which is 6 plus 2, so that's 8. And then 1 cubed plus 2 times 2. That's going to be the vector 8 comma 5. And then the magnitude of that vector, the magnitude of the gradient, is just going to be the square root of 8 squared plus 5 squared, which is the square root of 64 plus 25, which is the square root of 89. That doesn't simplify any further. So the maximum rate of change of this function at that point is the square root of 89. Second question, what is the rate of change of the function at the same point when y is decreasing 3 times as much as x is increasing. Okay, so they asked for a rate of change, meaning they're asking for a directional derivative. So we're trying to find the directional derivative. We know it's going to be the gradient, which we already found. Just the gradient of f evaluated at the point, which is just going to be the vector 8, 5, dotted with the unit vector of interest. Now, what direction are we going in? Well, it's kind of hidden. They're saying y is decreasing 3 times as much as x is increasing. So that means if x is going to increase by 1, y is going to decrease by 3. In other words, our vector here is going to be the vector where, well, let's see. If x is 1, y is going to be -3. Right? For every 1 that x increases, y decreases by 3 times that amount. So our unit vector here is going to be 1, -3 divided by the square root of 1 squared plus -3 squared. I like to bring that out in front, so I'm going to rewrite this as 1 over the square root of 1 plus 9 is 10. And then we're going to have our gradient of f, which was the vector 8, 5, dotted with the vector 1, -3. That's going to be 1 over root 10. Let's see, times 8 times 1 plus 5 times -3. That's going to be -15 plus 8, which is -7. So we get a -7 over the square root of 10. So again, what that's telling us is that in the direction where of the vector 1, -3, the slope of the surface is -7 over root 10. Okay. Moving on. Find del z del y for the equation e to the yz equal cosine of x times e to the x times natural log of x squared plus z cubed. So the point of this question is to use the trick that if we first rewrite this equation so that we've isolated everything on one side. So if we say, for example, f of x comma y comma z, doesn't really matter which side you bring everything to. I would probably bring everything to the left. So it's going to be e to the yz minus cosine of x times e to the x times natural log of x squared plus 1 minus z cubed. That's equal to 0. Then we know the equation is going to be that del z del y is equal to the negative of the partial of this with respect to y over the partial of that with respect to z, right? It's always, you just switch which one's on top, which one's on the bottom. So let's see. So that's going to be the negative of the partial of this with respect to y. So the derivative of e to the yz, or e to the stuff, is e to the stuff times the derivative of the stuff. The derivative of y times z with respect to y is going to be 1 times z. Over, now the partial, sorry, the rest. But there's no more y's, right? This whole thing is just x's, so its derivative is 0. This whole thing is just z's, derivative is 0. Divided by the partial of this whole thing with respect to z, which is going to be, let's see, the derivative of e to the yz is, again, the derivative of e to the stuff is e to the stuff times the derivative of the stuff. But now the derivative of yz with respect to z is going to be y times 1, which is just y. The derivative of all of this thing with just x's in it is going to be 0, and the derivative of negative z cubed is minus 3z squared. And that's your final answer. Not too bad. So definitely be on the lookout, right? If you see a bunch of stuff like that, right, we can just kind of ignore it because it's all x's. Sorry about this light being glaring over here. Can't really do much about it right now. Sorry about that. I'll try not to write in that area. Find and classify all critical points of f of xy equal to 2x cubed plus 3y squared plus 6xy. Okay. So we're going to find the critical points by taking the partials and setting them equal to 0. So fx is going to be 6x squared plus 0 plus 6y. And fy is going to be 6y plus 6x. I'm going to try and deal with the easier equation. So I'm going to use this equation. I'm going to get 6y equal to -6x, or just y equal to -x. And I'm going to plug that in up here and get 6x squared minus 6x, right? Plugging in -x for y equal to 0. You don't want to divide both sides by x, you want to factor out an x. So I'm going to factor out a 6x and get 6x times x minus 1 equals 0. So I either get x equal to 0 or x equal to 1. So if x is 0, then y is going to be negative 0. So my critical points are going to be either 0, 0, x is 0, y is 0, or if x is 1, y is going to be negative 1. Those are my two critical points. Now we have to classify them, which involves finding the capital D thing. So capital D, which is fxx times fyy minus fxy quantity squared, is going to be, let's see, fxx. So fx is 6x squared plus 6y. So fxx is going to be 12x. fyy is going to be 6. And fxy is going to be, well, either way, fxy is 6 or fyx is also 6. I would not simplify this, even though it's really easy to simplify it. It's probably okay here, but again, you don't really need to. So now let's figure out what's happening at 0, 0. If you plug in 0, 0, I get 12 times 0 times 6 minus 6 squared, which is negative 36. I don't really care about the number. I care that it's negative, because when your capital D is negative, that means you have a saddle at 0, 0. Let's figure out what's going on. 1, negative 1. So again, we're going to plug in 1 for x and negative 1. There is no place to plug in negative 1 for y. That's fine. So we're going to get 12 times 1 times 6 minus 6 squared. 12 times 6 minus 6 times 6 is certainly positive. So when it's positive, you have to do more work, right? You don't just say it's a max or a min. You have to be like, okay, well, there's your fxx. So fxx is 12, which is positive. Your second derivative is positive. That means you're concave up, right? Which means you have a minimum. So minimum at the point 1, negative 1. I strongly recommend when your capital D is positive, you take the extra step to think about, okay, what my second derivative is doing, whether it's positive and concave up or negative and concave down, and then what that means as far as whether I have a max or min. So concave up means min, concave down means max. All right, more questions. Show the following limits do not exist. Cool. So you should always try either x equal to 0 or y equal to 0. So, and sometimes both. So we try x equal to 0 here. Let's see what happens. Well, I'm going to have the limit. So when I do x equals 0, I just say, well, I know x is already equal to 0, so I'm just taking the limit as y approaches 0, because x is already 0, of 0 divided by 0 plus 2y to the sixth. But since y isn't 0, and I should have pointed out, if I plugged in 0, 0 to begin with, I would have 0 divided by 0, which means we need to do more work. Usually showing it does not exist means picking paths where you get different values. So here you have the limit as y approaches 0 of just 0, and the limit of 0 is 0. I will point out 0 divided by not 0 is 0, and the limit of 0 is 0. Let's try y equals 0. If we try y equals 0, we get the limit as x approaches 0 of 5x cubed divided by x cubed plus 0. But this simplifies to the limit as x approaches 0 of 5, which is equal to 5. So we're done. These two limits are different values. You might write words like the limit does not exist. The limit as xy approaches 0, 0 of 5x cubed over x cubed plus 2y to the sixth does not exist because we get different values along different paths. Cool. I think I happened to pick examples where picking y equals 0 and x equals 0 works for both of them to show it doesn't exist. That wasn't really intentional. Oh well. But here, if we pick x equal to 0, we get the limit as x comma y approaches 0 comma 0 of 0 over 0 plus 2y cubed, which again is the limit of 0, which is 0. And I did kind of what I didn't mean to do here. Oh well, sometimes I write the wrong thing. If we look at the path y equal to 0, we have the limit as x approaches 0 of x cubed times cosine of 0, which is 1 over 5x cubed plus 0. So this ends up being 1/5. And again, the overall limit doesn't exist because you have two different paths that go through the origin, x equals 0 and y equals 0, where the limit is equal to a different value. Other paths would have shown this as well, but we happen to luck out and have both of them where x equals 0, y equals 0 work. I'll point out that another path that would have worked here well would have been choosing x equal to y squared. Pick x equal to y squared for this first one, you get the limit as y approaches 0 of 5 times y squared cubed over y squared cubed plus 2y to the 6th. And that just ends up being 5/3. All right, that's all I have. Hopefully this practice exam was helpful. All right, good luck on your actual exam.